What I'm going to talk about today is the search for water and life on Mars, basically exploring the Mars underground drill and how to drill, where to look, things like that. Next slide, please. This is why we're all here. This is what I've been thinking about since I was 5 years old when I watched Robinson Crusoe on Mars for the first time. I realized how much I wanted to go to Mars. I want to go to Mars. I want to be there. I want to go there. Unfortunately, when I was 13, I took my first plane flight, and I read I, Robot and The Martian Chronicles, and I realized the last thing I want to do is go to Mars. I want to send other things to Mars. I want to build robots. I want to build things that are going to go to Mars and look for things that I think is important. We know Mars. We all thinking about it. Next slide, please. Why do we want to spend billions of dollars and thousands of people's time years to go to Mars and look for things? I'm part of the purpose-driven portion of NASA, as Dr. Zubrin talked about last time, not necessarily the vendor part. So there's got to be a purpose to everything we do and why we're going to go do it, because we think about moving the science forward and moving the engineering forward. So one of the reasons why we're going to go next, click, is comparative planetology. We've got Mars, we've got Earth, we've got Venus. Why are they so different? Why is Earth Goldilocks? Why is Mars dry? Why is Mars cold? Why is Venus really inhospitable? They all generated in the same portion of the solar nebula. They generated around, they accreted at about the same time. Why are they so different? Why is Earth perfect for life and Mars and Venus really aren't? We need to go there and find that out. Next, click. We also want to find resources to live off the land. It's not necessarily enough to understand that there's water on Mars. We make a joke at JPL. Every about 6 months, there's a new press release that comes out that we found water on Mars. And at JPL, we say, hey, we found water on Mars again. We know water's there. We know it's there. But the question is it accessible? How is it accessible? What do I have to go to go there and bring it if I'm going to send astronauts there? If I have to send a 200 kiloton bulldozer to go get the 1 kiloton of water that's there, it doesn't really make a lot of sense. So what it's there, how it's there, where we can find it, what we can do with it. And the third one is what I'm most interested in, is finding life. Now, life is a little difficult. Next slide. We talk all the time about finding life and what life is. On Earth, we have a very tough problem with extant life. The picture on the left is Allen Hills 84001. It's a Martian meteorite that was found in Antarctica in 1984, and a paper came out by Dave McKay et al. In 1996 saying that these little morphology inside the rock shows that there is Martian life in there. There's a big to-do. President Clinton was the first time in my lifetime that I remember a president coming out and talking about something that I was interested in terms of science, came out and had that press conference that's actually in the movie Contact about what an interesting time that we live in. Unfortunately, the more people looked at this rock, the more the evidence pointed to this not being particularly life, but it's probably an abiotic thing. There are still people that believe it's life, but the vast majority of scientists don't believe it's life. We've been having this conversation. This is probably the most studied rock in all of human history because of that. On the right are 2 places that I went to this summer. These are ancient stromatolitic beds. On the right, the furthest most point here, this is the Straley Pool Formation in Australia, and it shows evidence of these stromatolites, which we occasionally assume is life because they can be created both biotically and abiotically. So what you do is you look at the formation, you get other evidence associated with that. How long as it is, how long has it been there, what was the formation mechanism of it, what did it look like, how did it look, things like that. And then people will say, yeah, I think there's life associated with this, and then the community starts believing it. On the left is the same exact type of formation, but it's in Greenland. It's outside of Nook. And there's a paper a couple months ago saying that there was life associated with this rock. However, when you go to this particular location, you look at it and you're like, I don't see it. I don't see how this particular location, I don't see how these particular laminations in this particular rock showed there was life. And we're having a really long discussion in the scientific literature about whether there's life associated with versus there's life associated with this. So if you can imagine taking these particular examples and going to Mars and saying, I found life or I haven't found life, you can understand where a lot of the planning and things have to go for. Next slide, please. So finding life is harder than we think. Next. There really is no clearly defined definition of life, and this becomes problematic. The current best definition of life I think anybody has online is a self-sustaining chemical system capable of Darwinian evolution. But there's a problem with that. Next slide. Is that in this particular picture, there's only one thing alive. And those are the bushes, because that's a mule, and mules don't undergo Darwinian evolution. So the question is, if I can't even guarantee that the best definition of life I have in this particular picture, and I know those things are alive, how are we going to go to Mars and look for life? Next slide. So what we do is we go to places, analogs on the Earth, and we decide what we're really looking for is we're looking how is life distributed, what can I find, what can't I find. This is our postdoc, Haley Sapers. She's in a mine in North Dakota. She's about 4 kilometers underneath the surface. And what we're looking for is, we think this is a really good Martian analog. We know there's life associated with down here. So we go through there and we do a lot of testing on how we're going to go find life, what are we going to look for, how are we going to look for it. So right now she's looking at water that's stripped down through 4 kilometers. She basically runs it through a bunch of filters. We collect little particles in there and we bring it back to the lab and determine whether or not there's life associated with it. I can't do this on Mars when I go drill because I can't send Haley there. She's told me no. It's also a lot to actually drill through 4 kilometers and go it out and then have this particular piece of equipment there. Next slide, please. Different types of life measurements. You guys are having a discussion, I think, on Saturday by Carol Stoker. We'll talk more about this. A lot of people have proposed a lot of different individual measurements on what we're going to go look for life. We've all seen Star Trek. We've seen the tricorder. That tricorder is actually measuring something. What it is, I don't have any idea at the moment, but I do know that if I was going to go look for life, I would pick maybe multiple portions of this and different measurements, different instruments, different complexities, different styles of instruments. And I would go and I would look for one of these things and I would say, okay, this is probably life, this is probably not life. If you ever read anything, we've done a lot of press for Sherlock, and we're going to do a lot of press moving forward. We're very clear about using the word biosignature, potential biosignatures, potential biomarker. They all mean a little bit subtle different things. We continue to use that because we don't want to say, hey, I've definitely found life when we haven't found life. Next slide, please. Scale factors is another thing we need to consider. On the Earth, life is clumpy. Life, you can look through life in different, every scale bar you look at, life is really completely different. In the ocean, there are 4 or 5 different orders of magnitude on how much chlorophyll there is in the ocean. If I go down to an Antarctic sandstone, this picture over here, inside an Antarctic sandstone, when you're in the dry valleys of Antarctica, about a few percent of the rocks actually have life associated with them. All of that life is in one particular band on the top of the particular sandstone. It's hard for the people who know what to look for to go find a particular sandstone to show there's life inside of it. Cells on a membrane. The cells, all of the cells are basically little packs of carbon that are put on these membranes, and they're kind of very, very centrally located, and outside those particular things, there's nothing. This last slide that didn't come out very well is we've done some drilling in Greenland, and the organics that we find in the ice are clumpy as well. We would have thought, what we thought was, we would have thought there would be a stratigraphic layer of nothing but life, but it turns out that's not what we see. We see life in little packets on these, as we drill through the ice, and it's something we weren't very, very well expecting. But life is clumpy, no matter where we look. Next slide, please. So life as we know it really needs 3 things, and this is what drives us when we're talking about going to look for life on Mars. We know life on Earth needs water. We know it's got to be liquid water at least for a few portions of the year. That's the way it is in Antarctica. That's the way it is in subglaciers. That's the way it is in the bottom of 4 kilometers below the surface. We know it needs energy sources, and we know that it needs nutrients, which is pretty much why we've chosen to go to Mars in the first place, because when we look at Mars, we know Mars had water, we know Mars has nutrients, and we know Mars has energy sources, either chemical, volcanic, or solar. Additionally, we also know that life really has trouble with high radiation environments, and we know that life really does not like wide temperature swings, at least extant life that's viable. Next slide. So extant life, if it's there on Mars, is probably at a deep subsurface. The conditions on Mars are very, very inhospitable to life on the surface. a lot of radiation. It's very, very, very dry. It's the driest. Relative humidity goes to about 0 in the middle of the day. And we know that there's very little atmosphere, so liquid water is not necessarily stable on the surface. So we think that life would be available on the subsurface. If life started on Mars, it most likely went below surface. So where do we look and how do we look? Next slide. Well, where do we look? We need to find out how deep we're going to go because, as we heard in the last talk, it's very expensive to launch things. If I'm going to make a drill and I know that I'm only going to need to go 10 meters down into the surface, that's a much different system than if I have to go 100 meters under the surface. That 100 meters requires a lot more mass, no matter how you design the drill, and a lot more complexity, and that all costs money. And what we do is we don't want to necessarily spend more money than we actually have, because that's the way you go broke. In modern Mars, we've never gone underneath the subsurface. We have a few orbital assets that look at radar cross sections from the subsurface. We try to figure out what's actually in the subsurface. So this is a map showing pretty much where we think things are, at least in the equatorial regions of Mars. We know that there is methane. We've seen some methane on Curiosity. Ashwin's going to talk about that on Saturday. We've made this measurement. We've seen little bits of methane going up. We think that methane is coming from the subsurface. At least I believe it's coming from the subsurface. That subsurface then has to go. That methane has to go all the way through the overburden and get to the outer portion of it. Some of the things that make Mars inhospitable on the surface is an oxidizing layer. That oxidizing layer goes into the subsurface. The radiation environment. Radiation hits the surface. It kills a lot of things, and we don't know how far deep into the surface that the radiation actually goes. We do know that there are salty brines. We can see that from orbit. We can see there's evidence of subsurface liquid water in a lot of different places where there's salty. So we're looking for salty brines. We do know that there's lakes. There's evidence of a southern pole lake that Marsus has shown. And we do think there's a theoretical pure water table. Where exactly that pure water table is anybody's guess. We also know that in the northern latitudes, there's subsurface ice. So we know a lot of things, but we really need to know them better, because what happens is you've got to make at least one measurement to confirm the model, so the model can tell you where to go. And the model can show you where other places are and how you can really think about the planet. Next slide, please. This is a water map from Odyssey. This shows in about the upper meter where water is and how much water there is. You can see the poles. There's a lot of water in the subsurface, and this is in the upper meter. And it goes lower as you go lower in latitude toward the equator. You get less and less water in that upper meter. And that really does change how you're going to go about doing things. It's easier to get to the mid-latitudes than it is the high latitudes. It's also a much better environment to exist in the mid-latitudes than it is the upper latitudes. But if you want to get water and you need water to survive, you're going to have to design something to go to the upper latitudes, because that water is actually accessible, and I know how to get it. Next slide, please. At JPL, there's a couple projects that are currently going on. One is called Thor, once again, sorry for the acronyms, and Transmissive H2O Reconnaissance by Vlada and Bob Grimm at Southwest Research Institute. And what we're looking for here is that we're trying to understand where the groundwater table is before now, from the present to before now, to put models in. And we're just trying to design instruments to go there, and we'll actually be able to put something on the surface and look out and look in a particular region and find out where that water table is. We can go down tens or hundreds of meters, and this is a scouting exercise. There's two ways of doing a drilling mission. You can either send a drill mission, or you can send a scouting exercise to try to go into the subsurface, to look down at the subsurface, to get some idea what's going on there, then send the drill and drill down in there. This is a ground penetrating radar of sorts. It's actually an electromagnetic sounder. We put it on the surface, we turn it on, we then look in the subsurface. You can tell approximately where the water is. You would pick everything up, you would move it across the surface, you'd put it down again, you would look in that subsurface, you would map it out again, you would pick it up and move it, and therefore you can map something out. But that's a really complicated mission, because you have to be able to pick things up and move them along. Next slide. So this gets us to planetary drilling. Some of the things that we know about planetary drilling is mass. Mass is a problem. If you're going to, the more mass you send up, the more it costs. Next slide. And other things. I'm the principal investigator of Sherlock that was talked about before. Sherlock is an optical spectrometer. It turns out that the basic enemy of the optical spectrometer is a rotary percussive drill. And that basically is something that shakes like this. You don't ever want to put a spectrometer on something that shakes. We do it all the time. When we think about drilling, there's two ways of actually doing the drilling and doing the sample analysis of what you're looking at. The first one is instrumenting a drill. This is the Watson drill. Once again, wireline analysis tool for subsurface observation of northern ice sheets. And yes, we do have a guy at JPL that just does acronyms. We call him Acroman, and he's very, very good at it. Watson was designed for all of the instrumentation to fit inside the drill. And so from this, we have all of the drilling. There's another segment of the drill that's not present on here that has the flutes, and it grabs a core. But we have everything else automated in here. In fact, we have a Watson Sherlock-like instrument down here on this side right here. That's the laser right there. That we can actually look out of the sides and look as we're drilling down through the glacier. Everything else has got to be inside the drill. The power supply would have to be in the drill if you're going to Mars. All of the sample handling has to be inside the drill. All of the instrumentation has to be inside the drill. And that's what becomes very difficult if you're thinking about going to look for life. So a lot of the life instruments are going to be larger instruments that can't deal with vibration and can't deal with the environments that are inside this drill. So then your option is I'm going to take something that I'm going to go and I'm going to pick something up and bring it back to the surface. That becomes problematic as well, because then you've got to take your drill, you got to drill through something, you got to bring it back up, you got to drill through something, you got to bring it back up, you got to drill through something, you got to bring it back up, you got to drill through something and bring it back up. That takes a lot of time. That's a surprisingly large amount of time that you're going to have to do, and then you're going to have to figure a way to get the sample out of the drill and into the spectrometer or mass spectrometer or tricorder you've got on the surface, and that becomes very problematic. Next slide, please. So this is the way the Watson drill works. Worked at Summit. We have three different types of ice that we're looking at. One is firn ice, one is glacial ice, and it's not on this slide, but there's a portion of ice that's basically transition between firn and glacial ice. And what we found is it is problematic to continue to push things up and down through this drill string. That takes a lot of time. Time is equal to money because people have to run it. Basically, what we do is we drill down through about a 5 to 10 meter set of ice. A sample is collected inside the drill. The drill is then brought to the surface. The drill is then cleaned out, and then you hope that the borehole is compact, and that you can put the drill back in. You go back in and use some more sample analysis with it. On this particular slide here, this is where the instrumentation would be. So you also see that there's different parts of the instrumentation. If I had an instrument here that found something that was really cool, it could tell this particular instrument, hey, there's something cool here, you should look for it. But if I had an instrument here that found something pretty cool, and the instrumentation is here that showed wanted to see the same exact thing, it'd be very difficult to do, because then you've got to start bringing things up and bringing things down. It becomes very, very problematic for how you design a drill. Next slide, please. This is drilling in Kangaluska. Next slide. A tripod had to be set up. You can see here where we actually do have core. We do have a borehole stability throughout the entire borehole. Next slide. And this talks a little bit about the two different types of drilling, multiple types of drilling process. Drill segments, if you're going to only drill 5 to 10 meters, drill segments is not a bad way to go. It makes sure the borehole has stability. Otherwise, you've got to go through this wireline approach with the drill concept that's on the right for Asgard. Once again, sorry for the acronyms. And the drill goes down. Next slide, please. So that brings us to Sherlock. This is just a quick little pitch for Sherlock, because I talk about Sherlock all the time because I'm so excited to launch in July of next year and land in February 18th. Next slide, please. So once again, Scandalhammer, blah, blah, blah. Next slide. Keep going, keep going, keep going. Okay, so What we do is Sherlock is a laser spectrometer that does microscopic imaging. We have two different types of cameras on there. We've got a 30 micron per pixel color imager that's a reflight of Mali, and we have a 10 micron grayscale imager. Then what we do is we take a picture on the size of about 1.5 centimeters. We take a little laser, we scan a laser across the surface, and we can tell whether something, we can tell mineralogy, and we can tell whether it's got organic composition in that particular set. Next slide. We were asked later on to put on an extra camera. We came up with a really great acronym, Weird Appendage Tacked to Sherlock for Operations and Navigation. Couldn't do that, so then we had to go with the wide-angle topographic sensor for operations and engineering. So I've told you pretty much as we come up with the acronym before we come up with what the acronym stands for. And this is going to take really cool images, just like Mali does now. Next. We'll be able to take the rover selfies. We'll do the selfies for basically engineering purposes, make sure the wheels are okay, look at the belly pan. We'll be able to watch the helicopter get deployed, things like that. And then we'll also do microscopic imaging of layers and sedimentology and things like that. Next slide. Next slide. This is all available online. We can talk about it at leisure at the break. Next slide. So this is an example of what Sherlock does. This is a subsurface rock that we got from a Victoria Orphans group. It's a carbonate from one of the underwater hydrothermal vents. We wanted to see if there was life associated with it. So next slide. So what we did is we scanned Sherlock, and what we were trying to do is we're trying to understand what I talked about earlier about the distribution of organics in samples of what that looks like. So what we did here is we scanned a Sherlock-like measurement across the entire sample, and we wanted to see where the organics were in this particular rock. We had cleaned the rock off, we had cut the rock off because organics are everywhere. There's a lot of contamination everywhere. We tried not to measure the contamination. And what we found in this particular rock is that there was a lot of live organisms on the surface of the rock. You can see here lots of organisms on the outside of the rock. There's a fissure here. There's organisms here, which you would expect from where this particular place was. When you compare the topography up here to where the Sherlock scan is down here, you can see that organisms tend to go where there are fissures in the rock. And this is something that we would look for in the subsurface as we're going down. We also found something else really disturbing in this particular rock, and we couldn't figure it out for the longest time. This particular feature over here made no sense to us. It's out of place. It doesn't look like anything. I don't understand why biology would be there. And then a friend of mine said, that looks like a fingerprint. And we looked at it and we said, huh, it is a fingerprint. This shows you approximately how good of a resolution we can get. There's actually two fingerprints in this particular image. This is a fingerprint here. This is a fingerprint here. One of the postdocs, without wearing gloves, picked up the sample after we had cleaned it, and then we scanned it. It's a really cool thing because we needed a calibration target, so we're using his thumbs because we have examples of them. It's a joke. But it does show you the kind of sensitivity that we're expecting on Mars for organics, and this is what we would expect to see if we came across a hydrothermal environment. Next slide. Sherlock being put on the rover. If you get a chance, all the rover is being done online at NASA. You can go to YouTube and look for Mars 2020. They actually have an image of the Atlo. It's really cool to watch. It's really scary to watch somebody with a camera taking a picture of something else getting too close to your instrument, but that's a personal affliction that I have. Next slide. And I think I'm almost done. Just thanks 1,000 people. Thank you guys for listening. Too many people to thank. We have 1,000 people, including my son and daughter, who put up with me going to work every day. And I'd be happy to answer any questions.
If you can address possible ambiguities for biomarkers or potential evidence for life that you find, and I'm thinking of the Allen Hills meteorite, I'm thinking of the difficulty distinguishing between anorganic and organic methane. So when you find something interesting, how do you distinguish whether it is likely related to life or it isn't?
So that's an excellent question, and I was talking about this last night with people at JPL that work on the exoplanets, and everybody keeps talking about what is a biomarker for an exoplanet, and you know, people will throw things out like, oh, if we see methane in an atmosphere, like, well, I see methane in Titan. That doesn't mean I think there's things floating around on Titan. It always has to be a second measurement. There has to be multiple different lines of evidence. There just was a story last week on the Viking labeled release experiment, and how there are certain people that believe that there's life associated with that. But if you look at all of the other lines of evidence, if you look at every other measurement we've made, there's a better story to be told by using everything else. And so there's never going to be one measurement or one thing that's going to tell you whether there's life, yes or no. It's always got to be in concert with something else. If I measure, for example, in the labeled release, I measure a chemical signature, but I know there's no organics in that sample. I don't believe that signature came from organic life. So I've got to come up with a reasonable other explanation for it. So it's got to be multiple lines of evidence, and that's one of the reasons why we're doing sample return. Mars 2020 is the first part of sample return. We're going to cache some samples, upwards of 20 to 40, I forget the exact number, and we're going to bring those samples back because on Earth, what we learned from Allen Hills 84001 is that multiple lines of measurements have to be made on the same sample because you need to take everything together until we actually get a much better definition of life.
Thank you, sir. My question is about the slide that you showed with the drill going through overburden and into glacial ice. So you mentioned that one question is whether the hole will hold up.
Yes.
And I wanted to just say very briefly one experience we had with the proof of concept at MIT with this, and then to ask you a question about what is the likely path to flight to Mars for that. So we built a drill system for the Rascal Special Edition Mars Ice Challenge. And we were having difficulty with, we wanted initially to have a casing. We were worried about the hole collapsing.
Yep.
And then in experimenting, we discovered that when you drill into the ice and you have meltwater and the cuttings mix with the meltwater, the drill will case the hole with the mud, and then the mud will hold the hole together. And this worked out really well for us in the competition because we were able to lower a boom with a heater and a water inlet and bring up water, and it worked really well. Now my question to you is, given that Mars gravity is less, if this proof of concept is demonstrated on Earth with a higher gravity, do you think that the hole is even more likely or even less likely to hold up on Mars?
I think from our ice experience and from drilling, and we've done some drilling in the Mojave, with the same kind of, actually in Borgio Springs as well, with the same kind of equipment. It really depends on what you're drilling into. So we drilled into a sample that was basically anhydrate, and then underneath that was unconsolidated regolith. Great in the anhydrate. We went right through that, no problem. The borehole was fine, nothing fell in. The second we hit the unconsolidated regolith, because we were using a rotary percussive drill, and we were vibrating, we found that all of the unconsolidated regolith started falling in, and that was become the problem. So you have to design something to go to Mars if you're going to do the first drill that's got to take everything into account. And so that's where the design would have to take all that into account.
Given that near-term exploration is going to be closer to the equator and the Great Northern Ocean is north of Jezero Crater, how long do you think it'll be before we get to a place where we can look at the shores of the Great Northern Ocean and get something that will go down to the thousands of meters depth? A lot of people think our Archaeobacteria comes from thermal vents in the ocean. Something similar could have happened on Mars.
I think that the answer to the question is when will we actually go drilling on Mars, and that's an interesting question. There's a thing called the decadal survey that the science community puts together every 10 years and lays out the next series of missions. That's why we have Mars 2020. That's why we have Europa Clipper. The next decadal survey is getting done right now. And if Mars drilling is in there, if Mars subsurface gets in there in a high priority, in order to do that particular mission, you'd have to send at least one or two, I think, Pathfinder missions to demonstrate the technology. There's no reason why we couldn't do it by early 2030s. That technology exists, and that technology is good. It's just a matter of having the priorities and putting enough money into it. I'd never cost that out. I don't know how much it would cost to go 1,000 kilometers, my guess is pretty substantial, and that's probably early 2030s. We could literally do that with the technology we have today, and we could instrument it too, and we could do some really good science with it as well.
Thank you.